Welcome to ECE476, lecture number 10. In this lecture, we're looking at controlling motors with binary inputs using a Pi Pico. So part of the fun of being an engineer is you get to build things. Motors let you build things that move. Some examples would be valves, robotic arms, cars, etc. And several types of motors exist. The smaller motors often have digital inputs, which is this lecture. Larger motors typically have analog inputs, the coming lecture. This lecture looks at 4 different types of motors. The first type of motor we'll look at is a stepper motor. Here you specify how many steps the motor is supposed to go, and you control the position. By controlling steps per second, I control speed. The second type of motor is a BLDC motor. That's a quadcopter motor. If I control the pulse width, I can control the speed of the motor. Third type of motor is a digital servo motor. By specifying the pulse width, the Pico board can control the angle of the motor. And you might have noticed that the board I'm using in this video is different than the one we're using in class. This is the $14 version from GeeekPi for the Pico development board. Same idea, I'm just using the I/O pins, so a lot of the features of the Plus version I'm not using currently. So again, don't sweat it if your board looks slightly different than the board I'm using. So let's start out. How do you control different types of motors with a Pi Pico? Now the first motor we're looking at is the stepper motor. A stepper motor is a type of motor that's pretty common. It interfaces extremely easily with microcontrollers. It's actually a 2-phase AC synchronous motor. I've got the 2 phases, 2 sets of coils, each 90 degrees apart. So if I apply sine and cosine to the 2 phases, I get a rotating magnetic field. The rotor, the thing that spins, is a permanent magnet. So as the field rotates, the magnet spins with it. And it spins at a synchronous speed, which is why it's called an AC synchronous motor. It's designed for an AC signal, and the speed is synchronous with the rotating magnetic field. As far as what's inside the motor, you've got the permanent magnet in the rotor. This is a bunch of north-south, north-south. I've got a bunch of electromagnets in the stator. As I energize them, I can make this be a north or a south pole coming in. Then that all rotates on a shaft. So to drive it, I need to be able to drive current like 3 amps through the motor. The Pi Pico can't do that. So what you can do is buy an H-bridge. If you go on eBay or Amazon, you can buy an L298N stepper motor. Just search for the keywords Arduino H-bridge, and these come up, and there's other versions. This is a nice one that only costs about $3. It's capable of voltages between 5 and 35 volts. That's the voltage right here. This is what goes to the motor, 5 to 35 volts. Power and ground go here. This is what drives the electronics on the board. The logic levels, there's actually 2 H-bridges on here. This controls the left H-bridge, this controls the right H-bridge. And this goes to your motor. There's one coil, here's the other coil. So to connect it to your Pi Pico, what you do is you give it power and ground. This can be anything between 5 volts and 35 volts, capable of some current. I'm just connecting it straight to the 5 volts on your Pico board. This is one coil of the stepper motor. Here's the second coil. Now, if you're not sure which coil is which, what you can do is take the stepper motor and spin it. Take 2 leads and shove them together. If it spins freely, that's a separate lead. If it's the same phase, it'll go chick, 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 chick. What's happening is the motor is a generator. As I generate a sine wave, I see the high torque, high load on the peaks, the no load at the zero crossing. High load, zero load. There's a chick, 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 chick as you turn it. That would be one phase. And the other one, the 2 wires that are on the same electromagnet, same coil, go to the other phase. To drive it, I have 4 pins from the Pi Pico, and kind of notice I'm flipping the order. I don't go 16, 17, 18, 19. You need to flip the middle 2 leads. That is, well, we'll see that in a sec. In terms of software, what I need to do is drive the electromagnets. And there's a couple different ways of doing it. The motors that we have at NDSU are typically 50 poles. I've got 4 steps per rotation. That gives you 200 steps per rotation. Or 4 steps per cycle, 200 steps per rotation. Inside what you have is you have the rotor with a bunch of north-souths. If I energize, say this is the north-south, here's the east-west. If I energize this one, it attracts that guy. I then energize east-west, attracts the next one, and kind of rotates the motor. In terms of stepping, I'm trying to approximate a sine wave. Again, what I want is sine and cosine, makes this a synchronous motor, and it spins with a rotating magnetic field. There's a couple ways to approximate a sine wave. There's full stepping, half stepping, and micro stepping. The net result is with full stepping for our motors, you get 200 steps per rotation. Half stepping, you get 400 steps per rotation. Micro stepping is you get more than 400 steps per rotation. I try to approximate a sine wave with a bunch of smaller levels. We'll talk about that in a sec. So let's start out with full stepping. With full stepping, I try to approximate sine and cosine with a square wave. So what I do is I approximate the square wave as on, off, negative A, off. What's kind of happening, I've got a coil, A and C. When I want current to flow this way, I take C and ground it and apply voltage to A. If I want current to go the other way, I apply 5 volts to C and ground A. So the current's going left to right, right to left, left to right. I approximate a sine wave where the current bounces back and forth. Likewise on B, I do this 90 degrees out of phase, and the net result is to have 4 steps per cycle, and the stepping should go A, B, C, D. Then repeat. That gives you 200 steps per rotation. And kind of note that I want to go A, B, C, D, so the single coil is A and C. That's kind of why if I have the coils, I've got your A, C, B, D. That's what's connected to the motor. I don't do AC, then BD. I've got to flip these two. So when I flip them, I get CB, A, D. I go A, B, C, D, A, B, C, D. I've got to take these middle 2 wires and flip them. In terms of coding, what I can do then is I want to drive coil A, B, C, D, A, B, C, D. If I assign that a binary number, a 4-bit binary number, I can represent that as the number 1, 2, 4, 8, and repeat. In the code, I'm using a lookup table. That tells me which of these 4 pins should be on and off. So it could be A, B, C, D. Because I got the order backwards. Then in the subroutine step, I'm going to take whatever step I am in the table, mod 4. So if I'm at step number 0, I want to turn on A. I guess I got these backwards. D, C, B, A. It doesn't really matter. So I then turn on the first coil, second one, third one, fourth one. That's your step. Then to step the motor, I just output a number. Just start counting. So to see how that works, let's go to Thonny. I've got the different coils, and actually, just to be consistent, doesn't really make a big difference. I'm going to step through the table, telling me which one to energize, and then I'm going to count to 200. This has 200 steps per rotation, so as I count to 200, the motor should spin. When I get to 200, pause. So here's what that looks like. Again, it goes 200 steps, pauses, another 200 steps, pauses. And for stepper motors, they don't really know home position. I can sit there and twist it. I'm stalling the motor. Now I'm calling that 0 position. Goes 200 steps. That's 1 rotation. And you kind of see the coils here. The one side by side are 1 coil. So orange and blue are one coil, red and yellow are one coil. That is full stepping. There is a thing called half stepping. With half stepping, I do a slightly different approximation to a sine wave. I turn on channel A for 3 counts, off, C for 3 counts, off, A for 3 counts, off. By doing so, I wind up with 8 steps per cycle. And what the step should be, if I call this the first one, I should go A, AB, B, CB, C, CD, D, AD, then back to A. So there's the sequence I go through, 8 steps per cycle. What that gives me is 50 electromagnets, gives me 400 steps per rotation. And coding, I can see that as well. I'm going to use a lookup table. So this is A and B, B and C, C and D, and so on. In code, I can do that. So here's half stepping. It doesn't make a huge difference. If I do half stepping, I'm now going to count to 400, and now 400 counts is one rotation. It's a little bit slower because I have more counts to go through. If I don't count to 400, if I want to build a clock, I can just tell it, instead of going 400 steps, let's just go to, say, 100. That's 90 degrees. Or 50, 45 degrees. That is half stepping. There's also a thing called microstepping. So here the idea is what I really want to do is output a sine wave for A, sine wave for B, each one's 90 degrees out of phase. If I use PWM, I could approximate a sine wave by doing a PWM signal on A from 0 to 100%. Then when I want to go to minus A, I'll turn on C, 0 to 100%. Likewise for B and D. So in terms of coding, I'll set up A, B, C, and D as being PWM signals. Pick your favorite frequency, like 100 Hertz. Then your duty cycle. 0 is off, 65,000 is 100%. I'll use a lookup table that will define where I am on the different steps. So here's your sine wave. So this is for A. Usually at negative half. I want to go from 0% to 100%. 100% is 65,535. If I want to do 16 steps per cycle, split this up into 16 steps. The last 8 are all zeros. The first 8 is you approximate a sine wave with 8 steps, where the peak is 65,000. I'll then go through the table. I am going to go through the table mod 16 steps per cycle. Based upon where I am, that sets the duty cycle. B is 90 degrees out of phase. That's 4 out of 16. C is 180 degrees out of phase. 8 out of 16. D is 270 degrees out of phase. Now go through the lookup table with 800 steps. As you can see, as you go through the table, 800 steps, I do one rotation. So that was 800 steps. Another 800 steps. Same idea. Take your half rectified sine wave, split it up into 32 steps. So here's 0, here's 31, repeat. The last 16 entries are 0. This is your sine wave for the first 16. I now have 1,600 steps per rotation. Here's what that looks like. You can note that I'm going to count to 1,600. 1,600 steps is one rotation. So with stepper motors, I can get very precise angle control. In this case, using microstepping, I've got resolution of 1,600 different angles I can point to in one rotation. And with microstepping, it's basically unlimited. So that's one type of motor you can control with a digital input. And that's the beauty of stepper motors. They interface to microcontrollers really, really well. They want binary inputs. Okay, a second type of motor is a solenoid. This is actually just kind of like one part of a motor. Instead of rotating, it just goes in and out. What a solenoid does is an electromagnet. I've got a little spring. If there's no current, it's de-energized. This goes out. When I energize it, it produces a magnetic field and pulls the solenoid in. To power this, what I need is current. So on each solenoid, you check for the rated voltage, rated current. For this one, for example, it draws 1 amp at 12 volts. So I'm going to want to give it 12 volts. When I do that, connect to 12 volts and ground, it'll snap in. That's kind of like an electronic door lock. When I do that, the door's open. When I turn off power, the deadbolt goes out and the door's locked. So to power that with a Pico cannot do 12 volts, it cannot do 1 amp. But using a transistor, I can take the Pico and turn on off a switch that can handle 1 amp at 12 volts. So pick your favorite transistor, for example a ZTEX1051A. This is a transistor capable of 4 amps. It has a current gain of 300, which means 1 amp divided by 300, I need this to be at least 3.3 milliamps. Pick RB so that this is more than 3.3 milliamps. So one that works is 330. The actual current is going to be 3.3 volts from the Pico. This is a diode, meaning 0.7 volts. The current is 3.3 minus 0.7 over RB. So grinding that out, that gives you 7.8 milliamps. That's IB, 7.8. The max current that this can work for is I want to have beta IB is greater than IC. Some textbooks also use HFE IB, the current gain, basically, greater than IC. Take that multiplied by 300. This will now work for up to 2.3 amps. So here's a switch that'll turn on and off any device that needs less than 2.3 amps. Solenoid works. In terms of the range for RB, the smallest the current can be is 1 amp divided by beta, 1 amp divided by 300. The biggest it can be is 12 milliamps, because that's all the Pi Pico can do. And that actually gives you pretty good room for slop for RB. If I calculate the two limits, at 12 milliamps, it needs to be 780 ohms, 3.3 milliamps, 217 ohms. Pick anything between 217 and 780. I chose 330. Plus the solenoid is an inductor, it's an electromagnet. You need a flyback diode to save the transistor. If I do that, I can now turn on and off the solenoid. If this is 3.3 volts, this turns on, the solenoid snaps down. Make that 0 volts, the transistor turns off, the solenoid goes back to its rest position. So on, off. In terms of coding, again, just 1's and 0. 1 is on, 0 is off. And I don't have a solenoid to demonstrate for you, but you kind of get the idea. Third type of motor with the digital interface is a brushless DC motor, also known as a quadcopter motor. So brushless DC motors, I personally don't like the term brushless DC motor. This is actually a 3-phase AC synchronous motor. I don't think you can use phase and DC in the same sentence, but that's what they're called. So brushless DC motor, 3-phase AC synchronous motor, whatever. These have been kind of all the rage since 2010. They're extremely powerful, very small, lightweight, which makes them useful for quadcopters, RC cars, RC aircraft. They're small, inexpensive, powerful. For example, a 120 watt motor costs 20 bucks. That's the one shown. I can get a 1000 watt motor for 29 bucks. That's actually kind of impressive. 1,000 watts is 1.3 horsepower. You think about it, a horse can beat the crap out of a person. This is a small $29 motor. It can also beat the crap out of you. It's 1.5 horsepower. In terms of how to interface this to your Pi Pico, I need power and ground. It depends upon the ESC controller. I gotta look in the data sheets. The one I'm demonstrating, it needs 6 volts to operate. And current. These puppies draw current, so you can't really drive that from the Pi board directly. I need a separate power supply. The 3 leads go to the motor. They're fairly thick. It's going to be drawing a lot of current. And then there's a small wire. That's this guy right here. Again, the thick wire, that goes to motor. This goes to power. You can kind of tell because they're thick wires, it's going to draw current. These are small wires. There's no current. That's just the control signal. On those 3 wires, I've got red, black, and white. The red is 5 volts, black is 0 volts, common ground, and white is your control signal. Now what the control signal looks like is a pulse width. The frequency is between 50 Hz and 330 Hz. On power up, it needs to be 0.9 milliseconds. It's looking for that because if this is a quadcopter, helicopter, something like that, you don't want that puppy taking off on you on power up. It's waiting for 0.9 millisecond pulse. Once it sees that, it says, okay, I'm connected, I've got an idle signal, I'm powered up, I'm ready for something. Once it recognizes the 0.9 milliseconds, I can then vary the speed. 0.9 milliseconds is off, slow is 1.2 milliseconds, fast 3 milliseconds. So by varying the pulse width, I can vary the speed. So here's some sample code. I'm going to set the frequency to 50 Hz, PWM signal. I'm going to set the pulse width to 900 microseconds, or 900,000 nanoseconds. Wait for me to hit a button. When I hit the button, it's then going to enter this code and either go slow or fast. So kind of seeing how that works. Let's go over to Thani. There's my code. Pin 18 is my control input. On power up, it's 900 microseconds. And you kind of hear that. If I disconnect power, let's go down so you can see it. Disconnect power. What that did, that deedleet, deed, that first one, the deedleet, it's got power. The deed, it's got the correct power, 6 volts. The deed says it has the correct pulse width, 900 microseconds. So it is now waiting for an input. The input I want, I need a wire. It's waiting for pin 16 to go low, so I've connected up that wire. Hit the button. It now varies the pulse width between 1.5 and 2 milliseconds. And you can hear the speed changing. So that is a field DC motor. Vary the pulse width, I can make it go faster, slower, stuff like that. Last type of motor is a digital servo motor. Now these are kind of nice for robotics, for RC cars, stuff like that. It's a little servo motor that's been geared down. That gives you more torque and less speed. Motors are designed to spin, so when I control like the elevator, I don't really need it to go 2,000 RPM, just want to go up and down. That also gives you higher torque. And there's kind of 2 types of digital servo motors. Some output angle, kind of think like a robotic arm when you go to a certain position, the rudder of an aircraft or steering wheel, left, right. And the second one is speed for spinning. That'd be like the wheels of a car. Both of them have about the same interface. I have a pulse width. So with the motors, there are 3 wires coming in. The red wire is power. the black wire is ground, and the white or yellow wire is your control input. The control input is a square wave, frequencies between 50 and 330 Hertz, and the pulse width controls the speed, or actually controls the angle for this one. So 0.5 milliseconds is 0 degrees, 2.5 milliseconds is 270 degrees. So in terms of hardware, what you need to do is connect up your motor to power and ground. Power needs to be capable of 3 amps. Ground is just ground. The control signal is from the Pi Pico. That doesn't take any power. That's just a square wave, where the pulse width sets the angle. In terms of coding, well, here's kind of one way. I can have different push buttons, control the angle go up, go down, then the actual pulse width controlling the motor. Or I'm going to use this code. I'm going to set the frequency to 100 Hertz. 100 is a nice number in that range. My output is pin 18, a PWM output, and the duty cycle sets the angle. So initially, I'm going to start at 900 nanoseconds. For the first one and the second one. Start out. That's left over from old code. Start out at 0 position. Set the 2 pulse widths to 500 microseconds, 500,000 nanoseconds, and wait 2 seconds. I will then slew forward, start adding 2,000 to the pulse width until I get to 2.5 milliseconds. Wait, then come back down to 0.5 milliseconds. Wait 1 second. Then for the second motor, slew it forward, slew it back, wait 1 second. So here's what that kind of looks like. I am first sleeping 2 seconds. That's at the home position. I then go up to 2.5 milliseconds, back down to 0.5, go up to 2.5 milliseconds, back down to 0.5, and repeat. First motor, go to 2.5, back to 0.5. So the second motor is actually 180 degree motor. The second one also sees 180 degree motor. That's a digital servo motor. By setting the pulse width, I can control the angle. It's actually got some pretty good torque. The torque is due to all that gear reduction. In addition to angle control, there's also continuous servo motors. Same idea, but instead this spins, and the speed that it spins is related to the pulse width. So for example, this one, the power is 4.8 to 6 volts. No load current is 100 milliamps. That's just the wheel spinning freely. If you stall the motor, it draws more current, 500 milliamps. So you need a 5-volt supply capable of 500 milliamps. And the pulse width that you're looking for is between 700 and 2300 microseconds, 0.7 to 2.3 milliseconds. In terms of the control signal, I want to do a pulse width. In this case, 1.5 milliseconds is stopped. If it's less than 1.5 milliseconds, it spins backwards. That's like the car backing up. More than 1.5 milliseconds, it spins forward, car going forward. And there's kind of a dead zone in the middle. If you want the car to stop, it's 1.5 milliseconds, give or take. You can actually stop the car. The wiring is about the same as before. And the code, again, is about the same as before, except that 0 position is 1.5 milliseconds. So here's what that looks like. I'm going to set up pin 18 for a PWM output at 100 Hertz. Starting out at 1.5 milliseconds, that's idle. I'm going to go up to 2.5 milliseconds and back down to 1.5. I'll then go down to 0.5, then back up to 1.5. So here you see it's going clockwise, faster, slower, stopping, clockwise, faster, slower. And that is a digital servo motor that's continuous, really designed for like the wheel to drive a little RC car. So in summary, digital motors are pretty easy to interface to a Pi Pico. With a stepper motor, you can mimic a two-phase sine wave with 4 wires. With a digital servo motor, you can control the speed with the pulse width. You can control the angle with the pulse width. And kind of note that these motors are fairly low power. The stepper motor draws 3 amps at 5 volts, meaning 15 watts. The digital servo motor draws 2 amps at 5 volts, 10 watts. The continuous draws half an amp at 5 volts, 2.7 watts. That's the power in. And you can't get more power out than you put in. So each of these really limited to 10, 15 watts. Subtract the losses in the motor and the power output is actually less than that. If that's all you need, these motors are a really easy way to interface motors to your Pi Pico. If you need more power, well, that's typically an analog input to the motor. That's our next lecture. So that is lecture number 10 for ECE476 Advanced Embedded.